Point to finite limits. So we're going to talk about. I know, but they can approach a number. Yeah. Hey, why don't you let me teach the class? Okay, it works out better that way. So what we're looking at is that sometimes we can take the limit of a function as it approaches positive infinity, right? And the behavior of the function itself could approach a number. So that's why we call it finite limits. So even though x is approaching positive infinity or x is approaching negative infinity, it could still have a finite limit. Okay, and so these the textbook gives an example. So look at like the limit as x approaches infinity of the function 2 plus 1 over x. All right. Now here's what you've got to get used to. And then we'll look at this too, and then I'll explain why. Let me write this down. We're also going to look at the limit of this as x approaches negative infinity. Okay? The answer is 2 in both cases. And here's why. So if I graph this, and then I'll explain it to you. If I graph this in my calculator, what we have is a horizontal asymptote that occurs, at 2. So if I say 2 plus 1 divided by x and graph it, so right here at y equals 2 I have a horizontal asymptote. Alright, so I'm just going to sketch this graph real quick. X, y. And then when x equals 2, I've kind of got like this horizontal asymptote. And basically the horizontal asymptote means that y cannot equal 2, or it could come pretty close to it. Okay? And so if I graph this thing, what it looks like graphically is it kind of looks like this. As I come in from one side, it looks, one way, and if I go to the other side, it looks like it's approaching another way. All right. So as x approaches negative infinity, right? Because this is positive infinity in the x direction, and this is negative infinity in the x direction. As I come around this way, it approaches 2, and as I come around this way, it approaches 2.
But it doesn't hit 2, correct?
Well, here's the thing. I can justify this algebraically because, put on your thinking caps, 1 over infinity is basically pretty much equal to 0, isn't it? And 1 over negative infinity is basically equal to 0. And where we get that concept from, now this is an abstract concept, right? I can't prove it, but I can't disprove it. But just think about this for a second. If I take a pizza and I slice it up into 8 slices, the slice is 1/8 of the pizza, right? So, but that's smaller than the whole pizza. Now if I take that same size pizza and I slice it up into 16 slices, the slice is smaller. If I slice it into 32 pieces, the slice is smaller. If I slice it into 64 pieces, I have a sliver. If I slice that pizza infinitely many times, how big is the slice of pizza? 0. It's almost non-existent. So when I take this limit, if I were to plug in infinity here, I'd have 1 over infinity, which is like 0. 2 plus 0 is 2. And as I plug in negative infinity, 1 over negative infinity is 0, right? So then algebraically my limit would be 2.
I gotcha.
That's one scenario. So these types of things tend to occur when we have domain restrictions. So this is one example, 0 in the denominator, or in this case it's a little bit different. infinity in the denominator. So we're going to expand on that. The other one is square roots and stuff. So example number 1 in your textbook, ask us to consider the limits of this function, and I'll write the function down. It is x divided by the square root of x squared plus 1 as x approaches infinity, same limit, same function as x approaches negative infinity. Okay? Well, similar scenario. If I plug in infinity here on the bottom, I'm going to take the square root of infinity, which is still what? Infinity, right? It's still a really big number. And then here, if I do the same thing, if I plug in negative infinity, I square the negative infinity, which is positive infinity. So on the bottom here, I'm going to have infinity. The only difference is, what am I going to have on the top? Infinity and negative infinity. So now, are there any horizontal asymptotes?
Yes.
So what can I do before I move any further?
Graph it?
Let's graph it and see what it does. So I'm going to come into the calculator here.
Wait, can you graph infinity though?
Huh? Can I do what?
Never mind.
I didn't hear what you said. So I'm going to say x divided by x squared. Oh, we got to do the square root thing, right? Square root x squared plus 1. Do I have enough parentheses?
Yes, sir.
Interesting.
So 1 and then. Right.
So now I'm not going to talk about how you solve this algebraically, but if I have infinity on the bottom and infinity on the top of the fraction, we have to use a special rule. Do you guys remember what that rule was that I haven't taught you yet? L'Hopital's rule. And so we're going to skip that. But if you look at this graphically, what do you notice? If I hit the trace button, it looks like it's bounded from above and bounded from below. If I come around here, what would you suspect? What would you suspect the horizontal asymptote is?
1.
And then if I come in the other direction, what would you suspect the horizontal asymptote is? Negative 1. Now, without going into too much detail, if we were to apply L'Hopital's rule and we took the derivatives until we were able to take an algebraic limit, we would end up with 1 and negative 1. Does that make sense?
Yeah.
Another way to look at it too is when you take the square root of x squared, what do you really end up with?
X.
X. And so when,
You have to F1.
yeah, but when you're talking in terms of infinity, infinity plus 1 is just
Infinity.
infinity, right?
But we weren't talking in terms of infinity just now. We're in terms of that.
Yeah, we are, because we're taking the limit as it
Well, I know
approaches.
we are, but never mind.
You're right, Mr. Adams. So as so looking at the graph, this one is going to be 1, this one is negative 1, okay? And later on in chapter 7, we'll learn how to justify that algebraically using L'Hopital's rule, okay?
L'Hopital.
La Hospitals.
Sure. On the side. Wait. On